with the right idea to come along and just knock them down. That's what this is all about.
Okay, so here it is. Meet the villain of our story. I mean, just look at this thing. It's a 13th degree polynomial, a real mathematical monster. And the goal? Find the exact values of x that make this whole long mess equal to zero. For the longest time, that was considered a complete dead end.
So, why? Why was this thing considered unsolvable? Well, it's not that you couldn't get an answer. The problem was you couldn't get the perfect answer.
For years and years, the way to tackle this was with something called numerical approximation. Now, the best way to think about this is, imagine a super blurry, pixelated photo. You can kind of tell it's a cat, right? But you can't see the individual whiskers, the fine details. It's close enough, but it's not the real thing.
And this slide really hits the nail on the head. On one side, you have that blurry, inexact approximation. It's always got some errors. It's just good enough. But on the other side is the holy grail.
You know, for centuries, certain math problems were just considered impossible, unsolvable. But what if that wasn't actually true? Today, we're looking at a serious breakthrough that basically challenges a mathematical roadblock that's been standing for 200 years. Okay, let's just start with this monster. This is a 13th degree polynomial. And for a very, very long time, the idea of finding its exact answers, I'm not talking about close guesses, I mean the perfect solutions, was thought to be completely impossible. So why? What made this so incredibly hard? Well, to really get why this new development is such a big deal, we've got to go back and look at the huge wall mathematicians ran into almost 2 centuries ago. It really all boils down to something called Abel's impossibility theorem. And this thing is a cornerstone of algebra. It proved that once you get to polynomials of the 5th degree or higher, there's just no general formula, using things like square roots to find the exact solution. And this is the key difference, right? You've got 2 kinds of answers. A computer can spit out a numerical approximation that's super, super close, but that's still just a guess. It's not the same as an exact symbolic solution. Think of it like this. It's the difference between knowing a target is somewhere around here versus knowing its exact perfect coordinates, down to the millimeter. But what if there was another way in? A method that doesn't follow the old rules, one that finds a kind of secret path around these limitations that everyone thought were absolute. And this is where Ezwaidy's theorem enters the picture. It's a totally new way of looking at the problem. It's basically a tool designed to take these supposedly unsolvable equations and, transform them into something that we can solve, revealing those precise, exact roots. Now, the formula itself looks incredibly intimidating. Don't worry, we are definitely not going to solve this by hand. What's really important here is the idea behind it. It's a recursive process, which just means that each step of the calculation builds on the result of the step that came right before it. The best way to think about it is like a decoding process. The theorem takes all those numbers from that original messy equation, and then step by step, it calculates a series of special values. And these values, they end up revealing a hidden, much, much simpler equation inside that holds the key to everything. All right, so let's actually see how this works. We're going to watch this decoding process happen in real time with our 13th degree monster equation. So the theorem gets to work, calculating these special S values, starting with S0. And as it runs, the first few results all come back as 0. Now this might look like nothing is happening, but it's really the process just getting warmed up. And they just keep coming up 0 all the way through session 4. You're probably thinking, okay, is this thing broken? But no, this is actually a critical part of finding the solution. Each one of these zeros is another piece of the puzzle. And then, bam, we get a breakthrough. The 5th S value, S5, is not 0. It's a huge number, 13 to the power of 6 to be exact. This is it. This is the first secret key we've managed to pull from the equation. And right after that discovery, the process keeps going, and the next bunch of values, they go right back to being 0. And these zeros are just as important as the big numbers, because they're telling us something about the secret structure of that hidden equation. And then we get it. The second and final key is found at S11. It's an even more massive number, but it's perfectly precise. And get this, all the other S values for this entire polynomial turned out to be 0. Only 2 were not. So now we have our two secret keys, 5 and 11. What in the world do we do with them? Well, this is where you really see the power of this method. These two numbers, they are all we need. And look at that. This just brilliantly shows the transformation. That terrifying, screen-filling polynomial from the beginning, it just collapses into this beautiful, simple form. I mean, you can just look at it and immediately see that one of the answers has to be x equals 0. And from that simple little equation, we can derive this formula right here, which gives us the exact value for all 12 of the other roots. And these are not close guesses. These are the perfect symbolic answers, containing wild things like the square root of 199 and even the imaginary number I, which is just a fundamental concept in higher math. Okay, so this is way more than just a neat party trick for mathematicians. The big question is, why does finding an exact answer like this actually matter, in the real world? Well, it turns out that in a lot of advanced fields, precision is everything. Little tiny approximations, even tiny rounding errors, they can add up and cascade and cause big problems down the line. Having exact solutions is absolutely crucial for things like modeling quantum mechanics, for signal processing, and even for creating the unbreakable cryptography that keeps our data safe. More precision can lead to better models and way more powerful tech. So the most important takeaway is that this isn't a one-off trick for one specific problem. According to its creator, this is a universal key. It's a method that could be used on any of these high-degree polynomials, potentially unlocking a whole class of problems that we used to think were completely out of reach. And that, it really leaves you wondering, doesn't it? If a mathematical wall that stood strong for 200 years can just be sidestepped with a new way of thinking, what other so-called impossible problems are out there right now, just waiting for one new idea to come along and solve them?